Our next speaker is Neelam from India. Okay, she'll be talking about influence flow and antibody orientation on biosensor. Floor is yours. Yes, go ahead.
Hi, good morning, everyone, and I hope you are all having a very pleasant conference and stay in UAE. I have definitely loved this city a lot. So my topic of presentation is the effect of flow and antibody orientation on a biosensor, and it is a case study done using CA125 biomarker, which is a very prominent biomarker in the cases of ovarian cancer. My name is Neelam Vishwakarma. As you know, I am a joint PhD fellow at RMIT University, Australia, and ACSR, India. And I am in almost my finishing stages. So today I will be covering these major points here. My entire presentation will be focused on two things. First is what is the effect of flow and antibody orientation, and the second is obviously the biosensing part of the CA125 biomarker. As we all know, the ovarian cancer is nothing new to us. The entire problem of cancer is a very huge thing, is taking a huge toll on our healthcare systems in every country, irrespective if they are developed or underdeveloped. So ovarian cancer is generally present in the ovarian sites of the of your female gynecological systems, and it is one of the most fatal ones. These are few traditional methods which are being used, but obviously they are not able to provide a very high chances of early detection, as most of the symptoms in the ovarian cancer they are not presented until the cancer has spread to very late stages. So these are few statistics where we can see how the 5-year survival rate of this cancer is very critical as compared to even other types of cancers. For example, breast cancer, cervical, etc. And the earlier the cancer is detected, the best their chances of survival is. Like I said, I will be covering two things, the biosensor part and the microfluidics part. So why microfluidics? We all know that today the world is trying to move towards precision medicine, towards miniaturization, towards like whatever we can do to move the diagnostic in a very advanced stages, and that is where microfluidics plays a very important role. Coming on to the antibody orientation, so the antibody orientation molecule I used for providing the antibody orientation is the protein A. What it does is it enhances the binding capacity of the antibodies, and therefore overall improving the chances of antigen binding and the sensitivity. So I'm going to show the entire platform in these steps. This is the basic working structure from starting from building the linker molecule, which is aminated graphene sheets here, and then how we are moving and how we are testing the entire platform, and then we are going to this is a protocol being followed, and then we are going to compare how the microfluidics versus the non-microfluidic platform that is called static here is performing. These are some basic characterizations that were done for verifying that we have successfully prepared the amminated graphene sheets. So we have done a Raman shift, and like we know that graphene has a very distinct Raman spectra, and that is visible here. And then again, for UV spectra, for your XRDs and the XPS, where we have found that yes, the graphene was successfully prepared, and then we have found the amination part also very successful. Coming on to the next characterizations, these are our platform characterizations, which show how the platform has moved in different techniques. For example, the first in the FTR graph, we can see that this is a non-modified graph, and then with the sequential modification, we are able to see the increase in peaks of NH bonds, CN bonds, etc. Then again, we have done because it is a microfluidic study, we have done the contact angle variations also, so that we can ultimately conclude the microfluidic behavior of the platform. And then these are again the amminated graphene sheets images, where we can see that there is amination, because amination we all know is very important for antibody bindings. Coming on to the major second part, where we have compared the static versus microfluidic part. So we all know that microfluidics is able to provide us a very advanced medications, advanced healthcare opportunity. But what happens if we are able to compare the static and the microfluidic on the single platform? What is the you can say on-ground variation? What is the on-ground behavior in a single platform? So here you can see these are the microfluidics results and these are the static platform results. So what we observed is the behavior from both the platforms was not similar. What we observed was the static platform was undoubtedly, when we are doing the correlation regression, it was able to provide better results. But like we said, the static or the non-microfluidic platform, the stable platforms, they have their own disadvantages, as we cannot go into the miniaturization or the lab on the chip protocols with just drop-wise introduction of the samples. But with microfluidics, if we can create some systems, if we can bring those systems towards the same performance, then that is the ideal way to create the device manufacturing or the lab on a chip protocols. And this is here we are comparing the variations of data, like how our CA125 sensing modules were behaving in both the platforms. This is everything is with aligners. We thought, let us try another study where we don't add aligners. So like we all know, in biosensing fields, whatever agents you can use for enhancing the antigen antibody detection or the sensitivity, however the best way we can detect. So we can use any nanoparticles, we can use any biological materials for enhancing that, right? So here we have used linker as aminated graphene, and another thing which is antibody aligner, like I said, protein A. And then we have tried to find out what happens if we do not add the aligner. And then we are able to find this. So this is a comparison. In the previous ones, we saw that when we are using antibody aligners, it is able to provide us better or improved results, especially in the cases of microfluidics. So yes, in the cases of static platform or the drop-wise addition platforms, it was not providing much difference. So yes, because that is a stable one. So we thought, why? Like, why is it able to provide this much distinct, differentiated results? Like, obviously, we are using the regression, the R-square values as the indicator of if our calibration curves. So here it's 0.975, and then in the next one it's 0.94. So this is because of the shear stress that is present on the microfluidic platform. So whenever the microfluidics samples are flowing, they are able to uproot the antibodies in a lot of ways, which is not the same problem in the static platforms. And that is why we are able to see much distinction in the microfluidic platforms as compared to the static or the drop-wise selection platforms. Yeah, then we have, obviously, because it is a biosensor platform, we have to check a lot of parameters, a lot of how they are behaving. We have done pH studies, then reproducibility studies, and then interference with the other common proteins which are present in the bloodstreams. But another interesting study was, what we did was, what happens, like, how to find out if we don't add any of the linker molecule, that is the aminated graphene or the protein A. So this is the graph that showed us what will happen if we do not use any linker molecule, right? And then we did some serum sample analysis, that is the real sample analysis, because ultimately the goal of this biosensor platform will be to go out in the world and detect the real samples, and that is why we did some real samples. It was done in the, it was covering well the clinical limit for CA125, that is 34 units per ml. And with this, we were able to conclude that this platform as a whole, as a biosensor platform, was also working, but then it also provided us with very interesting observations when we are comparing both platforms. So this is the overall conclusion of the entire study. First, here we have the microfluidic and static platforms with and without antibody liners, just for comparison, where we can see that R-square values, how they are varying. And then this is the final a sensor platform of sensor performance, where we have showed the active surface area variations, the sensitivities of both the static and microfluidic platforms, and the LOD obtained. So yes, here you can see again the static platform is able to provide lower LODs because they are more stable right now. But what if we can find more such parameters like antibody liners? And that is what we are working on again in future. That like we varied one antibody liner, right? How else we can reduce the shear stress? And that is the conclusion of this entire study. This paper has been recently published in bioelectrochemistry, and this is my team at both the colleges. This is I'm working with Dr. Sharad at RMIT University and Dr. Suman Singh at CSI Chandigarh. This is my team, and you can contact me here if you have any more, if you want to connect in the future. Thank you so much. These are the acknowledgement. I'm really thankful to the I1 team for providing me with this opportunity. It means a great interaction session for me. It is a very blessed opportunity. Thank you so much.
Thank you.